Good afternoon, everyone, and thank you for attending our Tips for Designing Flex Circuits for Medical Applications webinar. My name is Ryan Wood, Content Marketing Manager here at Epic. Before we get started, I just want to let you all know that you'll be muted during the presentation. If you have any questions as we move along, please enter them into the questions panel, which is located in the webinar control panel, and we'll try to get to all of them at the end of the presentation. If we don't have time to go through all your questions, we will be sure to reply to you by email. Also, we'll be recording this webinar and posting both the recording and the slides on our website and YouTube channel. Our presenter today is Zachary Walker, our product manager of Flex and Rigid Flex circuits. His main responsibility involves interacting with customers' Flex and Rigid Flex products from start to finish. He assists in their product creation to ensure they can suit the customer's needs while still being manufacturable. Zachary addresses concerns or issues that may arise during any part of the process. He also oversees the quoting process for Flex and Rigid Flex PCBs. Zachary came to Epic with years of experience on the production and planning side of circuit boards. He's familiar with the aspects of production involving engineering and manufacturing, and has a bachelor's degree in chemical engineering from Texas Tech University with minors in chemistry, mathematics, and polymers and material science. So without further ado, I'll pass it on over to Zachary.
Thank you, Ryan, and good afternoon, everybody. So just as he said, we're going to be covering different tips for designing medical application-based flex circuits. Now, during this presentation, we'll be addressing things like mechanical reliability, flex lifetime, where just touching on key aspects of those like bend radius, trace layouts, and then just different best design practices for dynamic bends. And then we will move on from there to material considerations for medical environments. So things like what you'd expect a standard stack up would look like, or the standard materials within a stack up, and then what might be defined as like extra features or material choices that might be going beyond the norm. From there, it's a good move over to stack up and rigid flex transition best practices. So that's going to be the transition area for rigid parts where flex meets rigid, and then the design practices and rules that may go along with those. And for the flex side of things, we have stiffeners, where it's the transition of the stiffened area to the non-stiffened area, and different design practices for the stiffeners, and then considerations for things that may take place at that transition zone. From there, we'll move on to electrical performance and signal integrity challenges, things such as impedance, shielding, things of that nature. And then finally, we'll be closing out with manufacturability and compliance considerations for medical devices. And specifically, we'll be touching on things like IPC specifications and anything that may go beyond those in any way. So the first question is always, why use a flex circuit for a medical application? Why consider a flex circuit versus just straight wiring or any other alternative? And the go-to answer ends up being that flex circuits are just thin and lightweight in nature, just from the get-go, and that makes them optimal for many applications such as wearables and things like that, and they can be shielded just as easily by just a few alterations to the stack up. And so, as I said, they can end up being used in things like wearable devices, so things like wristbands, any form of tracking, anything of that nature for medical concerns, or they could be placed in clothing, so items that may be held close to the person and monitoring them that way, or even just generic medical monitoring devices, such as ones they may place on somebody's head to be able to measure electrical signals or other items like that. And then just general examination devices, so things you'd expect to see like scopes and lights and things that may be a little bit more specialized that don't fall into those other categories. So first, we're going to touch on mechanical reliability and the flex lifetime itself. And the first thing to start with on this, it is the most important thing I would say to consider for a flex lifetime and for mechanical reliability is the bend radius. And the reason being is if it ends up being ignored, parts are going to fail, and it can be sometimes difficult or even producing tons of headaches just trying to determine why a part failed when it may just be that the bend radius is being ignored and it is going past the limits of the design. And so it's unfortunate because bend radius is actually one of the easiest things for a flex circuit. Is one of the easiest things to calculate, to determine, to test, but most tend to get into the weeds of how complex a design can be and tend to just kind of forget about the bend radius, or in some cases may not even consider it to begin with. They may not know to consider it. And so from my experience so far, circuits in the medical industry tend to be dynamic flex. They tend to be ones that will bend for the entirety of the lifetime. And dynamic flex being anything, like I said, will bend over the lifetime, which a lifetime being considered infinite. And so a good example of that would be something like a ribbon cable for your printer or something of that nature where you expect it to move back and forth over the entirety of its lifetime. And for a dynamic flex, the bend radius is extremely easy to calculate. It is just for a 1 and 2 layer, 100 times the thickness of the board. That's the minimum bend radius. So can't go beyond that without ending up having a failure down the road. And so it's just something to keep in mind just from the very beginning. And so along that same line of bending, it's always best to also consider bends and how they relate to rigid or stiffened areas. So making sure that bends are not going on against rigid or stiffened areas. And if they have to at least use strain relief. So you can see on the image there that I've got a 2-dimensional mock-up, and you can see where strain relief will be placed against the rigid section that way. So if a flex circuit bends, it doesn't bend right there against the rigid section and crease, or even worse, break. And then below that, you can see a actual view of how we've placed strain relief along the edge of a board and how it ends up looking on a finalized product. From there, it actually does start getting into the design aspects of the circuitry. So you're going to avoid sharp turns and curves and traces, especially where a flex or a bend is going to take place. So any areas where the bend's going to occur, just have absolutely no turns and curves if possible, or just make them extremely gradual, make it easy such that the bend does not end up causing any issues whenever you try to bend it in those sharp turns. From there, for traces, you're going to also avoid what's known as the I-beam effect, which is where traces are directly above and below each other. This is a common effect that has been touched on many times, many presentations, and it's just a simple change just to stagger traces, prevent that added stress whenever a circuit's bent. So this slide, if you've seen a previous presentation, is probably going to look extremely familiar, and that's touching on avoiding critical vias and bend regions, being that copper tends to be a little less malleable, a little bit more rigid, so trying to bend in a via area will end up breaking vias at times, which for any critical vias that could cause intermittent shorts, or intermittent opens rather, and at worst even just definite opens where it's just immediately broken. So the only time we can recommend putting vias in areas that bend is where they're redundant or stitching vias. So vias that are, if one via fails or 2 vias fail, it's not the end of the world. And those are usually seen, for instance, in things like shielding and flex regions. And so like I said, any one of those, if they fail, it's not a big deal because you usually have 10, 20, 30 other connections elsewhere anyways. And then you'll also want to, on the assembly side of it, avoid sharp corners or areas in a housing or assembly where a crease can develop. Creases will end up deforming the copper, and once trying to undo a crease, it'll actually cause the copper to break, which ends up with an intermittent open. And so all turns should be gradual. They should follow the bend radius that I mentioned earlier, and just try to make it as gradual as possible whenever possible. And then once more on the design side, you want to use hatched ground planes instead of solid planes where possible. This is more key for dynamic applications due to the higher strictness for the bend radius. And this will seem a little contradictory because there are opportunities where you have to only use solid planes, things like impedance controlled applications or shielding. And so it'll seem contradictory, but it's just something to keep in mind whenever trying to design a board. So if you have impedance or if you have shielding, it's solid. If you have neither of those, use hatch ground planes, and it'll at least buy you a little bit of flexibility. And then when possible, for both flex or the flex area of a rigid flex design, to use a one-layer flex. And the reason being is you can design a stack up such that the copper is in the middle of the stack up. It allows for a neutral bend axis, meaning the copper is not being stressed in one direction more than the other. So moving on, so for material considerations for medical environments, we're going to cover kind of the basic structure of flex to start with, which is starting from the very top, polyimide coverlay and the coverlay adhesive. And then underneath that will be your copper, then your polyimide core, and then any internal adhesives as needed where it might be needed to contact and laminate on other layers of copper, and then it will circle back around to the polyimide coverlay and adhesive once more. And just as I said, almost all core and coverlay materials are polyimide based. That's just the nature of flex. That's the flex industry. Those are just almost entirely polyimide based. Adhesives can vary a little bit more. You can end up with acrylic or epoxy, and even more extreme polyimide based adhesives. However, we can only support acrylic and epoxy, and most manufacturers will probably only support acrylic or epoxy. And your choice between those will end up going back to anything in your environment that they may interact with. So if you have chemical interactions in a lab setting or temperature requirements for any sort of testing, it's something to consider whenever you're going through whether or not to choose acrylic or epoxy. Regarding the copper, one of the key elements to a medical flex, and really even just a dynamic flex in general, is using RA copper, with RA copper being more suited to bend over the lifetime of a flex, contrasting to the default ED copper, electrodeposited. And while adhesive-based cores can be available where an adhesive-based core might save on money or availability, dynamic flex, since it requires that larger bend radius we touched on earlier, the 100 times the thickness, it can kind of work against adhesive-based cores because adhesive-based cores have the added thickness. And so almost entirely we will recommend for dynamic flexes to use adhesive-less based cores. Now, you're limited on all those items, on the polyimide, on copper type, coverlay, adhesive, and then you start getting a little bit more freedom from there. So For instance, in stiffeners, you can do polyimide-based stiffeners. So if you have a ZIF connector, or you just need a thin stiffener, or if you need a thicker stiffener, if you need something, say, 030, 040, then you might move to FR4 instead. If you need specialized ones for heat sinks or a certain material contact concern, then you might have stainless steel or aluminum. And then expanding even higher technology than that, there's shielding, where you can add, like I was saying earlier, shielding layers or shielding films in areas where signal interference may occur. So for instance, imaging equipment, MRIs, things of that nature, which we have consulted on before with some customers, where it'll be entering an MRI, it needs to be shielded, it needs to not have any noise to the sensing equipment, and so you have to introduce some sort of shielding into the board in order to prevent that. Moving on, we've got stack up and rigid flex transition best practices. So stack ups will ultimately almost always end up being the easiest or the hardest part. And what I mean by that is a simpler design will obviously have an easy stack up. A 1-layer design will have an easy stack up compared to this 10-layer design that I have here on the side, where it's an expressly more difficult stack up, and where if you don't know manufacturing, then you might not know how to lay up the stack up here as shown. So we're just going to give a few rules just to make things as easy as possible when you're designing your stack up. So first, you want to make it symmetrical. So in a rigid flex, you want your flex layers to be centered. And so as you can see on the right, 10 layers, got 3 centered flex layers, and we've got an even amount of spacing, or attempted spacing, on either side as best as possible to kind of center the both of them. You'll want to consider all items, so coverlays, stiffeners, things of that nature. It's always critical to keep those in mind, because if you forget about those, then it can really interfere with bend radius and then design, and then it just kind of domino effects from there. And then, as I said, you'll want to design with the dynamic bend radius in mind from the very beginning. So discussing housings, fittings, anything of that nature, you want to keep design bend radius in mind. And then for materials, where if you need more exotic materials, or if you're worried that a material may be too exotic, or a thickness may be too outside of a realm, or even if it's just something a little bit less common, like higher copper weight, and you're worried about availability, it's always best just to come to us from the very, very beginning. We can help with stack up design. We can supply stack ups after a brief meeting. It's no issue for us to help in that area. So for the transition zone, it is the area defined where the rigid portion of the design ends and the pure quote unquote flat flex stack up begins, or vice versa. And so this zone is actually where most problems end up being derived. Earlier, I pointed out strain relief needed to prevent it from bending back. So that's the mechanical challenges you may run into in those areas, where it may have sharp edges, it may crease against that if it's bent, so you'll need strain relief almost always in a rigid flex design. And then by design, even with the changing material properties in that transition zone, it can introduce a lot of extra rules regarding trace routing and via placements and things of that nature. And so the key rule, probably the most important than others, if only because it is the one that we most commonly see forgotten in designs, is the distance of vias from the edge to the transition area. So for a rigid flex design, this means keeping vias no more than, say, 0.50 from the via to the transition. And then for stiffeners, while it's simpler, it is still mechanically best to keep it at least 0.10 from the via to stiffener edge. And then going back to rigid flex designs, another key takeaway that seems easily overlooked is to always keep circuitry away from the edge of the transition. And typically you want 0.25 distance from circuitry to the edge. And this is less for mechanical reliability and more for manufacturability. It allows for tolerances that may be needed whenever you're imaging and doing your external image processing with dry film and things of that nature. And so you'll see on this design, for instance, this is a good example of both, where they've kept their vias away from the edge. There's no exposed circuitry that you can see of that's against that edge that could have caused a concern or could have made it difficult to manufacture. So moving on, we've got electrical performance and signal integrity challenges. And given most medical applications, it's no surprise that they will require signals or a greater demand of electrical performance than some other applications or industries. So like I was saying earlier, MRIs, evaluation tools, scanning equipment, things like that all end up necessitating high-speed signals, impedance control, shielding, just the absolute most security and noise prevention just to avoid crosstalk, interference, things of that nature, because the last thing anybody wants is for their medical equipment to be producing errors. And so impedance can actually be the trickiest thing among those. It's, if you've ever seen the calculation for impedance, it is incredibly complicated. And that's coming from somebody with a minor in mathematics. It can be fairly complicated and intense, especially if you're not privy to high degree mathematics. And so you'll end up relying on either those intense calculations using a known calculation software, or using stack-ups perhaps that have been tried and tested to achieve controlled impedance values. And so, as I was saying, impedance designs are going to require one of those two things. Preferably a known stack up, so it's going to have known impedance values, design, trace width, spacing, core thicknesses, copper thicknesses, and it's going to be having been manufactured, tested, so on and so forth, until a reliable value has been output. Or you're going to have to rely on an impedance calculator, which calculators, it's all theoretically correct, but sometimes calculators can be a little tricky and might not produce right, hit the nail on the head sort of impedance. So we end up falling back to known stack ups. First and foremost, it's just, like I said, mini builds, a lot of experience, and it just ends up being the preferred way of approaching stack up creation for impedance. So as you can see here, for a differential impedance within. And there are key rules for impedance control. So I touched on one of these earlier. You're going to use solid copper ground planes when possible. It's going to essentially just be better for signal integrity for impedance to be used that way. A question we've had brought up many times is if shielding, in the case of shielding films, if they can be used with impedance, but unfortunately, they're not exactly made to be able to perform a reference ground that impedance needs. So shielding, like shielding films, can't actually be used for impedance reliably. You'll want to keep consistent trace spacing throughout the design. Any waivers in trace spacing, movements, things of that nature are going to introduce issues with your impedance. And you'll want to consider how it moves from rigid to flexible sections and how your traces are done there. Many times, if done improperly, you'll have to end up having to change trace thicknesses to account for impedance differences between rigid and flex sections. But in those sorts of cases where it becomes more complex, it's always best to come to us first, so that way we can help to calculate and evaluate where that might be needed or if it's needed. And then speaking on shielding and designed where they might be required or where interference might occur, like I was saying, MRIs, evaluation equipment, things of that nature, you're trying to keep signals out or signals in, and you're trying to make sure that no erroneous results are introduced. And so you'll end up using shielding film or copper solid layers where it's essentially, as I said, preventing that interference from interjecting into your design whenever it's undergoing any testing or use in the field. Or even in more specialized cases, you might require stitching vias or which I had shown earlier, or something to that nature where you're trying to isolate signals entirely, and you'll do so by creating those stitching vias, a picket fence, so to speak, and caging the entire design such that there's a Faraday cage effect and all signals are trapped within the board and kept from having signals creeping into the board as well. And so for manufacturability and compliance considerations, the unfortunate nature is that medical devices are also usually extremely high tech, which is only unfortunate because then they start requiring things such as blind or buried vias, shielding, vias in flexible sections, and trying to maintain a dynamic bend radius, which it ends up being juggling plates and trying to figure out how many you can juggle without dropping any. It could be incredibly tedious to do, but that's the reason we end up suggesting and hammering down that it's always best to consult a board manufacturer, especially if you're trying to introduce multiple things of that nature all at once, because many of those things may end up conflicting, like trying to add shielding, which adds thickness, but then also trying to maintain thin boards for dynamic flexing, or concerns for vias and flexible sections, but you need them because you need the interconnects or things of that nature. Things can tend to hit against each other and at worst create impossible scenarios, but at best an incredibly difficult scenario, and that's kind of where we excel, is trying to give advice on those and hopefully turn impossible designs possible. So with that in mind, it is also important to bring forward your compliance considerations. And what I mean by this is typically we only consider for any design IPC specifications, 6013, which is the standard for flex circuits, 2020, 2223, which is the guideline for flexible circuits, 4452, the ENIG standard, and any standard beyond that among IPC standards. But we, unless told otherwise, we won't be considering the FDA standards or ASTM or ISO or other standards that may apply strictly to a medical circuit unless we're told. So it's always best to bring it up at the very forefront to say that a design has requirements among those standards that may be non-standard to normal board fabrication, or even if you are unsure if it's normal board fabrication standards or not, just bring it to us. We can discuss it and we can see if it pertains to fabrication or manufacturing in any way, or if it's just something that strictly is a reliability or standard for testing. We're always happy to help on any standards of that nature. So in closing, medical devices are difficult. There's red tape, FDA standards, testing, compatibility standards, design requirements, and that's not even getting to manufacturability. That's not even getting to the actual production of the board. So it's always best to keep us in mind for that sort of thing, to let us consider and help with the manufacturability so that way you can handle the red tape and the standards and things like that. And it can be difficult as well with flex circuits, just because whenever things improve over time, they get smaller, they get more lightweight, they get more high tech, which means more challenges, more complexity, and that means designs ultimately end up requiring more assistance. So anytime that you have different requirements, impedance, non-IPC standards, dynamic bends, anything like that, it's always best to just come to Epic from the very beginning. We can advise as needed for assembly, for standards, for design best practices. We help in any way we can, just to at least get you across that finish line and ideally get you to testing your boards.
Thank you, Zachary. Now, while he reviews the questions that came in, I want to briefly mention some of the additional products we offer here at Epic. For over 70 years, Epic has designed and manufactured custom-built-to-print electronic products. Our expertise not only lies in printed circuit boards, but in custom battery packs, overmolded and other types of cable assemblies, flexible heaters, high reliability user interfaces, and EC fans and motors. I will turn it over back to Zachary to go through some of the questions that came in.
All right. So I've got one question here. What is the bending lifespan of a dynamic flex? Can I expect it to fail after 10,000, 100,000 bends? That's a little bit of a difficult question, and reason being is IPC, when they consider dynamic flex, they like to use the term infinite. It's not truly infinite, but that's the term they like to use. And so it can be kind of difficult to nail down an exact, say a board's good for 100,000 bends or 1 million bends. It could be difficult to nail down an exact number, and it can even be more difficult because you start having to consider the layer count, how dramatic of a bend is it, or thickness of the copper, anything of that nature. And so you can't exactly nail down a lifetime and failure point for bending. Usually that's only done through testing, and with testing it could be difficult to do, is I guess where I'm drawing back to, and it will just require pure mechanical field testing if possible. All right. I need to use LCP for my flex material due to the material requirements. Can this be done? So unfortunately, we cannot support LCP, which is shortened for liquid crystal polymer. We are always welcome to looking over designs that may require it. However, we have in the past experienced designs that have been brought to us with LCP as the key performance material that they may need. But generally, since we can't supply boards with that material, it kind of circles back to us evaluating the designs and seeing, okay, does the design truly need LCP? Can we deviate to just standard polyimide? And sometimes the answer is yes. Sometimes material considerations are too strict and you end up finding that standard polyimide works just as well as LCP and that you don't need to spec out an expensive exotic material just to have your design function. Sometimes it'll just function normally with polyimide. All right. Why is RA copper used? RA copper, which stands for rolled annealed, it's used primarily because it's better for bending. RA copper is a copper that, when compared to ED, electrodeposited copper or treated copper, RA has been heat treated and treated in such a way that all of the grain direction is oriented along one axis that can allow for bending and can improve bending even in certain cases. And so many flex designs will end up using RA copper because sometimes you need that 1 or 2% extra flexibility. It's not a quantifiable extra flexibility, but it's sometimes you need that little bit of guarantee. So many designs will use RA copper, and many designs will even specify grain direction in their drawings for RA copper. My design calls for 85 ohm impedance. Do you have a stack up for that impedance? So I believe we do have an 85 ohm stack up. Generally, we will provide stack ups and be able to supply stack ups for things like 50 ohm single, 75 ohm differential, 100 ohm differential. There are certain standard quote unquote impedances. However, some designs might require unusual ones that may end up going outside of those for whatever reason. So we may not have the tried and practiced stack ups that we've manufactured for those impedance values, but that doesn't stop us. We can fall back to the calculator just as easily and be able to calculate it, and then at the end of our design be able to test it to ensure impedance. And so in that case, 85, I believe we have a stack up, but if you require a special impedance beyond that and we don't have it on hand, we could at least say that we can calculate it for you and then at the end provide testing to ensure that we're within tolerance for those impedance values. Unfortunately, I believe that's all the time for questions that we have today, but I do want to thank everybody for coming out, and if you have any further questions, please feel free to reach out to us.